Welcome to EDU World Space.
All right, so let's start this problem. So we've got a cylinder. See that r squared is equal to 1. But I wrote this incorrectly. So let's look at the actual region in question, right? So it looks like we have this circle. However, x is bigger. X equals 0 is something that divides this plane, right? So we're only looking at this right half. This right half here. But if we also take a look at z equals 0, it gives us that y equals 0. Okay? So that means we're also restricting our domain like this. So what we're really looking at is this portion here. So theta is going to run from 0 to pi over 2. Okay? So this guy here should be a pi over 2. Okay? Now let's look at the rest. So r is 0 to 1, great. Theta we just talked about. Now let's look at z. Why did I write z as less than or equal to r sine theta? Well, it's because I want to change everything in this problem to polar. Okay, so all the triple integrals that I'm going to be doing are going to be in terms of polar coordinates. And I can see that my z is going to be bounded like this. It's going to be bounded above by y and below by 0. But I can write y in polar coordinates as r sine theta. Okay, so once we start writing this integral, it's hopefully going to make a little more sense. So the mass is the triple integral over the density function here. So this is our density function in polar. Okay, so I've switched this guy here, and I've switched this guy here as well. Right? These are r sine theta. Okay, and z is just going to be z. So z stays the same as in the density function. And now we integrate with respect to z, and then we have our polar part of the problem. So we need our r dr d theta. And then again, we're using a computer algebra system, or AKA just a calculator, to get this as our answer. Okay. Now we have to look at this guy here. So remember, x bar is equal to 1 over m triple integral of x times rho dE. Okay. So this guy is our x. This guy is our density function. So that's what's going on here. And again, everything is in polar. So these bounds are the same as always. We've got our z, r, dr, d theta. And again, plugging this into a calculator, we get this. Same idea for y bar and z bar. So this guy is our y. This guy is our rho. Again, we get this as our answer. Once again, for z bar, it's equal to triple integral 1 over m triple integral over e z rho dE. So this guy here is just z because we can't write it in polar coordinates, and rho is given by this guy here. Again, calculator. Okay. And finally, this is our moment of inertia around the z-axis. So this formula, remember, is a triple integral over e, x squared plus y squared times the density function. Okay, so here's our density function. And r squared is x squared plus y squared, obviously, in polar coordinates. Again, we have our dz, r, dr, d theta. Okay, and again, just plug into a calculator, and this is our answer.